Okay, so let's do question B now. So we're trying to find out the voltage AB. So VAB is going to be VAB is equal to VA minus VB. So the voltage at position B minus the voltage, other way around. Voltage at position A minus voltage at position B. So what's the voltage going to be at position B? This one's really easy because the electrons come out of the battery here and they haven't gone through any resistors yet by the time they hit point B. So there's no voltage drop, which means that the voltage at position B is just going to be 15 volts. Okay, so let's write that down. So voltage at position B is going to be 15 volts. Now the voltage at position A is a little bit more tricky and it's going to be a little bit longer to figure out. But before we get started on that, let's take a look at what happens to the voltage as it moves through the circuit. So I've picked out red here to show that the voltage, to show the voltage. So I'm going to color the line to tell you what the voltage is going to be. So that might not make sense until I actually show you. So the voltage at first, one sec, mess around with these colors. So the voltage at first is going to be 15 volts, right? So the voltage is going to be high. So I've made the voltage represented by red. So the voltage is quite high until it hits this resistor over here, and the voltage decreases. So we'll make it orange from this point on. So the voltage has decreased, now it's orange, and let's see what can happen here. Now the current, the electrons, right, can move in 3 different directions. They can go here, they can go here, or they can go here. So which way are they going to go? Well, they're going to go through all 3 different ways, but let's just follow this path right now because we're concerned about what happens at point A. So let me just get these colors straight. Okay, so the electron is still going to be orange as it goes through here, because it's still got a little bit lower voltage than what it had over here. So over here would have been 15, and over here, I don't know what it would be right now, but it's lower because it had to go through the resistor. So it goes through the resistor again, and this time the voltage is going to decrease. So the voltage is going to be yellow now. And remember, the electrons don't travel down this way towards point A, because there's no way to go from point A back to this battery. The electrons are always trying to go back to the battery, right? So they exit the positive terminal of the battery and they go back to the negative terminal of the battery. So since there's no way to go back to the battery from point A, the electrons just don't travel down that way. So they'll travel down this way instead, like this. Then they'll go through this resistor, lose some voltage again, and they'll become, let's say, green. So they're really starting to cool down now. The voltage is really starting to decrease. And we keep on going, keep on going, keep on going. And now we hit another point over here. And you might think, well, the electrons can go up like this, or they could go this way. Well, we haven't really drawn what happened up here. So when the electrons were here a while back, they would have already poured down like this. And they would have turned green. So they could meet up with these green ones here. So the voltage would have dropped. And you might be wondering, why doesn't it turn yellow? Well, the answer is that at any given node, like this node over here, the voltage of the electrons has to be exactly the same. So from this path, we know that the electrons turn green. So based off that deduction, there must have been a larger voltage drop across this resistor. So let's imagine that like this up here, was 15. This one became like 12. So this is 15 volts, 12 volts. This is like 9 volts. This is like 5 volts. So we had a 3 voltage drop over here across the 100 ohm resistor, and then a 4 voltage drop across the 200 ohm resistor. But over here, this specific 200 ohm resistor had a 12 minus 5, that's going to be 7 volts drop. So the voltage drop across a resistor isn't always just based off the resistance, it also depends on the path. Anyway, that's a little bit more advanced. It's not really that important to know at the moment, but just for the sake of illustration here. So we'll finally go across this blue resistor, or sorry, the resistor, this last resistor, and now the voltage is going to turn blue, and it's going to go back to the battery. And of course, if we do this one over here, we will fill that out, fill it out, fill it out, and we'll get blue over here. So you can see again that this 160 ohm resistor actually had a bigger change in temperature than the 200 ohm resistor. Why? It's not because the 160 ohm resistor is, way stronger of a resistor. It's actually weaker, but because of the path that it has to take. And we can talk more about this later, but for now, that's just how it goes. Okay, so the voltage at A, what's it going to be? Well, there's no electrons going there. So you might say, well, the voltage is equal to 0. That's not true. The reason why it's not true is because if you had taken something, like let's say you have a ground connection, so you have a connection to ground, and you connected it to point A, well, now these yellow electrons actually have a path to travel, right? They can travel down here, and they can go to ground, which they're happy to do, just as happy as they are to go to the battery over here, right? So there is actually a voltage here. And what is that voltage? Well, we can use there's a couple of different ways to think about this. It's not 100% clear, but it's not 100% clear in my head anyways. So I just use different ways of thinking about it to make it make sense to myself. But one way to do it is you can say, okay, V is equal to IR, right? The voltage drop across a resistor, this resistor in particular, is equal to the current that goes through that resistor multiplied by the resistance value. So the voltage drop across this resistor is equal to 0 times 30, because there's no current, there's no electrons moving down this way, right? So the voltage drop across that resistor is 0. So what does that mean? It means that there is no difference between the voltage at this point over here and the voltage at this point over here. And if there's no difference, that means that this voltage must also be yellow, right? So, so the voltage at A is equal to the voltage over here, which we just said was 9 volts, but I just made that number up, right? So it's not actually 9 volts. So that's kind of an explanation of the theoretical stuff that's happening. Let's actually calculate the real voltage here. Okay, so, alright, so how are we going to do that? Well, what I'm going to do is I'm going to figure out what the current is that's moving through this resistor. If I can find out what the current is moving through this resistor, I can figure out what the voltage drop is going to be across this resistor. And I already know what the voltage drop across this resistor is going to be. I'll show you in a second how I know that. Okay, so I'm just going to delete that. Okay, whoops. Okay, I went a little too far back. Okay, so from the previous question that we did, we know that the current moving through here through this resistor here is 150 milliamps. So the voltage drop across that resistor is equal to the current moving through it times the resistance. The voltage drop across that resistor is going to be equal to 0.15 amps, also known as 150 milliamps, times the resistance value. So 1, 2, okay. Oh, okay, that's okay. So the resistance value here is 20 ohms, right? We're talking about this resistor here. So VD is going to equal, what is that going to be? Times 10, that's 1.5, that's 3 volts. So we're going to lose 3 volts across this resistor. And since we started off with 15, that means that the voltage here is going to be 12. Wow, how did I know that? Okay, so the orange voltage is 12. Okay, next we need to find out how much voltage drop there is across this resistor, and then we'll be able to figure out what the voltage is here. So that's kind of a tricky part. How do we find out how much current travels down that orange path? Okay, so there might be other ways to do this, but this is how I would do it. So our circuit looks like this. Like that. Like that. Like this. And like this. And remember, there's no current moving through point A, so it's not, it doesn't contribute to the resistance of the whole circuit, right? So we're just going to leave that out of there for now. Oh goodness. Okay. So what I want to do is find out the current moving through this branch. And so what I'm going to do is I'm going to find out how much current is moving through this whole thing over here. And then I'm going to split that current again between here and here. So that might not make too much sense, but just follow along and you'll see what I mean. So first thing I'm going to do is I'm going to put these two resistors together. And since you can just, in your mind, you can imagine sliding this resistor up and then down onto this one. So just imagine this riding the wire all the way down, right? If it can merge together like that, that means that they're in series. So let's just go ahead and merge them together. So if I can find my cursor, there we go. Okay, so I'm going to get rid of this, and I'm going to put that here, and that means that these two resistors come together, and that was a 100 ohm resistor and a 200 ohm resistor, so that becomes 300 ohms. Okay, now this one over here is also, this one's 200, this resistor right here. So what I'm going to do is I'm going to put these two resistors together, this 200 ohm resistor and 300 ohm resistor. And I know this can seem confusing, like what is this guy doing? But just follow along and you'll see what I'm doing by the end of it. So I'm going to put these two together, and the way I always imagine it is like these are two vines. So like you have one vine like this, and this other weird kind of vine like this. And I imagine that it just swings down until they're both overlapping each other. Okay, so these two here are in parallel with each other because they start off at the same node and end at the same node. And so we're gonna put those two together. So, and we're gonna have a single resistor like this, and we're going to keep this one here, and that's going to go like this, And this one here is going to have a resistance equal to 200 parallel 300. And in the previous video, we actually figured that out. I think it was 125, but let's actually do the math again. So it's 200 times 300 divided by 200 plus 300. That's going to equal 6 times 10 to the 4, and that's going to be 500. Yeah, so that's going to be 1.2 times 10 to the 2. Yeah, which is 120. Quick maths. Okay, so that's 120. So, okay, that's 120. Okay, and this one over here is 160. This one is 40. And this one is 20. Okay, so we know that this one over here can be slid this way and then back up here to join this one. So that means that they're going to be in series. So if we redraw this, it's going to look like this. Then like this. Okay, so this one was 120, this is 40, so that's going to become 160. And this one over here is also 160, and this one is 20. So what we have here is a battery where the current coming out of it is 150 milliamps, and that 150 milliamps has to get divided between these two branches. So branch 1 and branch 2, right? This branch and this branch. Now, since these resistors have the exact same resistance values, the current is going to be divided exactly in half. So what that means is 75 milliamps is going to go through here, and 75 milliamps is going to go through here. Okay. So if we look back at the original schematic, we know that 75 milliamps goes through here. And 75 milliamps, the other 75 milliamps, has to be divided between these two nodes, right? Because this guy over here, this 160 ohm resistor, is a combination of all this stuff over here. Okay, so now we'll go back and redraw the schematic again. Yeah, it's a huge pain, but that's what you gotta do. Okay, so I think we can go from this one here, this diagram. So this diagram over here, we have the central one, which goes 75 milliamps, and this node releases 75 milliamps, the sum of 75 milliamps across these two other pathways. So how much current goes down this way and how much current goes down this way? Well, whenever you have a situation like this, first you gotta erase this stuff. So whenever you have this kind of situation where you have, okay, we know that a total of 75 milliamps has to travel down two different resistors, and then they come back together like this. We use this formula. So I'll show you the formula in a sec, but let me just label this. So it's 300 ohms, and this is 200 ohms. Okay. So if you want to find out how much current is going down this 300 ohm path, what we do is we use this formula. So the current down our resistor or through our resistor is equal to the current, sorry, not the current, the resistance of the other path. So this is the other path, right? This is the path we're trying to solve for. And this 200 ohm path is the other path. And that's going to be divided by the sum of the resistances multiplied by the total current that you have to share. So that would be 200 ohms in that one path, and then the sum of resistances would be 200 plus 300, and the current that they need to share is 75 milliamps. So that's going to be 2 over 5 when you simplify it, 75, and I feel like this is a pretty easy, that'd be 120, right? Oh, did I I think I may have done some math wrong here, but we'll just keep on going with the wrong math, but the logic is still sound. So that'll be 120 divided by 5, that's 120 divided by 5, that should be, well, let me just use a calculator now, since I've already goofed it up once. Did I goof it up though? We'll see. Okay. So 75 times 2 divided by 3. Oh, sorry. 75 multiplied by 2 divided by 5 is 30. Okay, so 30 milliamps. So we know that 30 milliamps go down this pathway, and the rest have to go down this way. So that would be 45, right? So we start off at 75, 30 go down this way, and 45 milliamps go down the other way. So going back to our original diagram, we know that this 200 ohm resistor is going to have 30 milliamps go down it, and this one over here is going to have 45 milliamps. And you might be a little confused because over here we have 300 and over here we have 200. That 300 comes from adding these two, which are in series. So it's this path versus the other path that's adjacent to this middle guy right here. Okay, so let's clean up a little bit. Okay, so let's get rid of all this. Alright, so we know that 30 milliamps goes down this yellow path. If 30 milliamps go down that path, we can find out the voltage drop here. So the voltage drop across a resistor is equal to the current moving through the resistor multiplied by the resistance of that resistor. So the voltage drop in this case is going to be equal to 30 milliamps multiplied by 100 ohms. So VD is going to equal, well, that's going to be quite small. Let's see. So let me just pull up my calculator here. So 30 divided by 1000 multiplied by 100. Oh, okay. Yeah. So 30 milliamps is 0.0. This would be 300 milliamps. This would be 3 milliamps. So 0.03. 1, 2. Is that right? 1, 2. Yeah. That's correct. Okay. So 30 milliamps multiplied by 100 ohms. So you have to get the units right. You can't multiply milliamps. You gotta turn it into amps. So the VD is gonna be 3 volts. Okay, so that means hey, I got it right again. That's crazy. So the voltage drop across this resistor is 3. So we started off at 15, then we lost 3 here, so it became 12. Then we lost 3 again, so we became 9. So the voltage in this yellow section, is in fact 9 volts. And so that means that the voltage at position A is also equal to 9 volts. So we can finally answer the question. VAB is equal to VA minus VB. VAB is equal to VA. VA is 9 volts. VB is equal to 15 volts. That's this red section. So VAB is equal to -6 volts.